Welcome to Math 31. This is Lesson 7, Area Between Curves. So pretty similar to what we were doing before, but just going a bit further. So I'm going to draw attention initially to these four different graphs. Now, as you know, or should know at least, that when you're dealing with the definite integral, it always gives you the area between the curve and the x-axis. So in this case, this area would be positive. Whereas, if you were down here, because you're below the x-axis, the area is going to be negative. But where things get interesting is when you look at situations where you're trying to get the area between a curve. And if you were to consider that the area formed by this was A1 and this is A2, the area between, that is delta A, is going to be equal to area 1, which goes all the way to the x-axis, minus A2. Makes sense. You just get the difference between the two. Now the shape for the fourth graph that I've got here, the bottom right, is identical. So you have this. The only thing is that you're below the x-axis. But it still works the same way. If this is A1 and this is A2, if you want to get the difference between the two curves, delta A would be equal to A1 minus A2. Now you're thinking, why not A2 minus A1? Well, it doesn't really matter. If you did it like that, you'll get a negative answer, and then you'll have to adjust, because the answers for these, when you get the area, when you're talking about area between two specific curves, your answer should be positive. So if you went A1 minus A2, you're taking the little negative minus a big negative, so when you reverse the signs, you will get a positive answer. And as I said, we should get positive answers for these when you're taking one curve relative to the other. But this gives us a method then. So we can go on to do questions like this. Get the area between the curves, the quadratic, x squared plus 1, and the linear, 5x plus 7, looking like this. So we want to get these values there. And to do so, we note that the linear is g at x, the quadratic is f at x, and we need to find these points, at least the x values. And by getting the area underneath g at x in that interval, and then the area underneath f at x in the same interval, and subtracting, we should end up with an answer. So what I'm going to do is find the intersection points. Algebraically, easiest way, I think, is to ask the question, where is f at x equal to g at x? So we get x squared plus 1 is equal to 5x plus 7. You get a quadratic out of the deal. So x squared minus 5x minus 6 is equal to 0. So that when you factor, you'll get x minus 6 times x plus 1. So our two x coordinates, when you solve each one of these, are going to be x is equal to 6 or x is equal to negative 1. And that matches what we see in front of us on the curve. Now, with respect to the y-coordinate, you can, if you want, find the y-coordinate. And if the question says find the intersection points, you should get the y-coordinate. So you actually have a full ordered pair. However, it doesn't matter a whole lot because it's going to be not affecting this, because we only deal with the x values for this sort of interval. So really, to get the area from negative 6, or positive, negative 1, excuse me, negative 1, to positive 6, it would be the definite integral from those values, so negative 6 or negative 1 to 6, keep wanting to say that, and we recognize that the g function is on top. So all we do is go g at x minus f at x. And had you done the reverse, then all that would happen is you would get a negative number for it. So plugging in, this is going to be negative 1 to 6. The g function is 5x plus 7 minus the f function is x squared plus 1. Then dx. Mopping it up a little bit, tidying it up, negative 1 to 6, we'll get 5x, and then minus x squared, and then 7 minus 1 is plus 6. Dx. And then I'm just going to get a bit more space to deal with this one. So bring up the new screen to work it down. So from negative 1 to 6, sometimes I press this wrong button, it does all that. I'm going to write this one in descending order. I'm going to put the x squared term in front even though it's negative. So negative x squared, and then plus 5x, and then plus 6 dx. So we take the antiderivative of it, so this becomes x to the 3, and then negative 1 over 3x to the 3, plus x squared, and then 5 over 2x squared, and then plus 6x, and from lower limit negative 1, upper limit 6. So negative 1 over 3, 6 to the 3, plus 5 over 2, 6 to the 2, plus 6 times 6, minus negative 1 over 3, negative 1 cubed, plus 5 over 2, negative 1 squared, plus 6 times negative 1. Now you can pretty much make this go right through your calculator without a lot of fuss. So I'll enter it like that. Negative 1 divided by 3, open bracket, 6 to the exponent of 3, plus 2.5, bracket, I just write that as 36, plus 36 again, and I get 54. And then minus, so negative 1 divided by 3 times negative 1, because that's what negative 1 cubed would be. You can do that directly. Plus 2.5, well, negative 1 squared is 1, so that's not going to affect anything, and then minus 6. And when you turn this into a fraction, you'll get negative 19 over 6. So this becomes 54 plus 19 over 6. And then either keep it in whatever form or fraction you want. That's going to be 57 and 1 over 6. Or if you wrote it as 343 over 6, you'd be fine as well. But that's the idea. Now let's take a look at a related question. Find the area between this quadratic and 5x minus 3, which looks like this. Now you could do this one essentially the same way, but the first thing that might disturb you a little bit is the fact that it's dipping below the x-axis in parts of it. So you're thinking, oh, that's a negative area. Does that affect anything? Answer would be no. It doesn't affect anything, because when you're dealing with one curve relative to another curve, it's only their orientation relative to each other that matters. It doesn't matter if they're above the x-axis or below. And you see that this one is, in fact, these are the same curves as the previous graphs. Only thing is 10 units down, a vertical translation of 10 units down. If you take a look at the numbers, the other one was x squared plus 1, this is x squared minus 9, etc. Like in the other one 5x plus 7, now 5x minus 3. So therefore, the area is going to be equal to 57 and 1 over 6. Same answer. Now, you would have otherwise done it the same way. I mean, there's no problem. You do f at x minus, or in this case, g at x minus f at x. It works the same. But that's the idea. So we don't care where we are relative to the x-axis, only where we are relative to each function. Now let's do, there's two more questions that we have on the lesson notes. I'm just going to do the one because it's really, the second one is pretty redundant. But this one is got some use to it. We have two sections for between this cubic and the linear. And that's what makes this question somewhat noteworthy. This is A1, this is A2. Now, the total area means again that we need to get the sum of A1 plus A2. And then you're thinking out there, well, why not put absolute value signs around that? And of course, you could do so. It isn't really necessary, however, because these ones should be positive as it is, just because they're always positive when they're relative to each other. So I'm not so much worried about any sort of negative value for this. And A1, well, we're going to have to get the intersection points. You might be able to read that off the graph. Some of them you can, in fact. But I still would do it the old way. So the intersection points. So where is f at x equal to g at x? So we take our x cubed minus 2x squared minus 11x plus 12, and we set it equal to 12 minus 3x. Now I'm worried because it looks like it's going to be a cubic, which will require some form of division. However, when we do all the numbers on this, we'll get x cubed, bring it all over to the left, and then we'll get minus 2x squared, and then the 3x gets added on, so that's our minus 8x, but then the 12s are gone. So this spares us from having to do any form of division, because all we need to do is factor out the x, giving us x squared minus 2x minus 8 equal to 0. And then x, this factors into x minus 4, x plus 2. Check it if you don't believe me. So x is equal to 0. Set each of them to 0. You get x equal 4, x equal negative 2. These match what we see in the graph. So there's our negative 2, there's our 0, and there is our 4. Now the thing is, you must break it into two sections. And you also want to be aware that the g function is the linear and the f function is the cubic. So for the first interval, a1, the cubic function's on top. So this is going to be f at x minus g at x. So I will indicate it as such. So a1 is equal to the definite integral from negative 2 to 0 And because of the nature of this graph, the f function's on top, so we would write this as f at x minus g at x dx. So it will turn into, for us, 0 to negative 2. Your f function is x cubed minus 2x squared minus 11x plus 12. And this one is going to be minus 12 minus 3x. dx. Negative 2, 0. Do all the work on it. You're going to get an equation you've seen recently. I'm going to go there fairly directly. X cubed minus 2x squared, negative 11x, watch your signs carefully, but minus negative 3x will give you minus 8x, and then the 12's minus 12 is gone. So this is what we get. The same equation that we got when we were solving for the intersection points. So this will then become, when we take the antiderivative of it, we get x to the 4, 1 over 4 x to the 4, minus x to the 3, so 2 over 3, minus x squared, and that's 4, 8 divided by 4, 8 divided by 2, and that's from 0 on top, negative 2 on the bottom. And then we just set it up and go. This one would be 1/4 times 0 to the 4 minus 2/3 times 0 to the 3 minus 4 times 0 squared minus 1/4 times negative 2 to the 4 minus 2/3 times negative 2 cubed, and then minus 4 times negative 2 squared. And the first part of this expression, of course, is going to be 0, and then minus what we get for the other. So this is 1 divided by 4, bracket, negative 2 to the exponent of 4, minus 2 divided by 3, open bracket, negative 2 to the exponent of 3, minus 4, open bracket, negative 2 to the exponent of 2. And you'll get 0 minus negative 20 over 3. So when we take care of that negative, this turns into positive 20 over 3, and that is our A1. Now A2 would simply be the definite integral from, this case, 4 on top to 0. And we would, in this setup, have to recognize that the g function is on top. So this becomes g at x minus f at x, and then dx. So A2 is equal to, from 0 to 4, our polynomial is going to be 12 minus 3x minus your x cubed minus 2x squared minus 11x plus 12 dx, which is going to simplify to 4 to 0, the same polynomial that we had for the previous one, except the signs are different. So we get negative x cubed, we'll get plus 2x squared, and then we'll get plus 8x dx. And then anti-differentiate, and we'll get, we'll put up the bracket, negative 1/4 x to the 4 plus 2/3 x to the 3 plus 4x squared, and then all this dx. I'll just take this down below, because now when we, in this, oh, sorry, we got the dx's, we've taken the antiderivative, 0 to 4. So we now substitute in the 4, negative 1/4 times 4 to the 4, plus 2/3 times 4 to the 3, plus 4 times 4 squared, minus the whole thing, negative 1/4. This will be a little tight. It didn't give myself enough space. But you see where this one's going. Plus 2/3 times 0 cubed, plus 4 times 0 squared. So that will be equal to 0. And then the rest of it, when we put it through our calculator, negative 1 divided by 4, open bracket, 4 to the exponent of 4, plus 2 divided by 3, open bracket, 4 to the exponent of 3, which is your 60, that is 64, 4 cubed is 64. You obviously don't need to put the exponents in if you don't want, plus 4 times 4 squared. When we do all this, I get 128 over 3 minus 0. So therefore A2 is equal to 128 over 3. And we could now say that the total area is equal to 20 over 3 plus 128 over 3. So the total area is equal to 148 over 3 square units. I won't bother with the last question, which is really just a repeat of it, and nothing really new happening with that. But that's how these go. So the next lesson that we look at will be on the substitution method. So we will get develop some skills, not so much related to the area, of course, that indirectly, but more so that we can expand the number of questions we can integrate well. So thank you for your time.